Hello guys, welcome again to this session. Thank you for taking your time to get this course. So my name is Anthony Uwandu-uzoma. So today we're going to be taking a walkthrough towards epidemiology. So we're going to be looking at how you can get started with epidemiology. So the first thing we're going to look at is the different types of study that we have. The different levels of study designs that we have in epidemiology. So basically, by definition, epidemiology simply means the study of disease distribution and disease patterns in a specific population. So epidemiology deals with 5 W's: the who, the where, the what, the why, and the when. So these 5 terms about a disease or a condition, that is the focus of epidemiology. Now, the domain of the domain of epidemiology can be divided into 2 broad categories. You have the descriptive epidemiology and you have the analytic epidemiology. So for the descriptive epidemiology, it deals with the first 4 W's, which is the what is a disease, who has the disease or who has the condition, where is the disease or where is the condition or where is the event happening, and then time, when is the event happening. So these 4 questions are answered by descriptive epidemiology, right? So now when you talk about why is a disease happening, then you talk about analytic epidemiology. When you ask why, then you talk about analytic epidemiology. So analytic epidemiology tries to answer the questions about questions like what is the cause of a disease, what are the risk factors of a disease, right? So those are the 2 broad categories. So now we need to look at the 4 broad types of study designs that you have in epidemiology. So we have the descriptive epidemiology, like I've said. Then you have the descriptive studies. Then you have the hypothesis testing studies. So hypothesis testing studies, like I said, they are also known as analytical epidemiology. They try to find out if there's a relationship between A and B. And an example of that is the ecological studies, and you have the case control studies, and then the cohort studies, right? So those are hypothesis testing studies. Then you have the other type of study design, which is what intervention studies. In intervention studies, you are looking at causation, you are looking at efficacy, effectiveness of an intervention, effectiveness of a drug. All right. So whenever you read any question in the exam that seems to uh, uh, describe an intervention or whereby a drug is being tested, then just know that that is an intervention study, okay? And there is only one example of intervention study, that is called the randomized control trial. So whenever you hear an intervention is being mapped out or a drug is being tested, just know that the answer is intervention study, or the answer is randomized control trial, okay? Cohort study and case control study and ecological studies are all classified as observational studies because they are always either looking backward or they are looking forward. So if the studies is looking backward, okay, by backward I mean that the client has the subject already has the disease, and then you're looking backward, maybe at the patient folder, or asking questions, taking history to find out what caused the disease. That is called a case control study, right? Now, on the other hand, if you're looking forward, that means you are following the patient up in the future um, to see what might have caused a disease. That's a forward-looking study. Okay, that means that the type of study the type of that type of study design is called a cohort study. That means what? That the client is exposed but doesn't have a disease right now. So you are trying to follow up the client to see if this client you can develop disease. So that is called a cohort study, right? Now, the measure of risk of a case control study is the odds ratio. So you have to link these things in your brain at this early point. The measure of risk in a backward-looking study, that is in a case control study, is called the odds ratio, right? I'm going to discuss that later. Now, the measure of risk in a forward-looking study is called the relative risk, or you can also call it the risk ratio. Okay, so now two of them are interpreted a little bit different, but they are almost similar. So now, for a backward-looking study, when the odds ratio is greater than 1, that means for a case control study, when the odds ratio is greater than 1, you can say that there is an association between the exposure and the outcome. An example of exposure is maybe smoking. Now, an example of an outcome might be lung cancer, right? So if you read any question in the exam and you see, just check, and they say the odds ratio is greater than 1, okay, but the odds ratio is like maybe 2, just know that there is a positive association between this A and B, right? Now, if the odds ratio is less than 1, that means there's a negative association, right? So, but I'm going to go more details into that, but just know that. Also, the same thing with the relative risk. If the relative risk is more greater than 1, there's a positive association. If it's less than 1, there's negative association. So, but I'll go more into details in subsequent videos, right? So, just for you to know. Now, the last type of study design that we have is called the methodological studies. So, methodological studies, they are not primary studies, they are all secondary studies. So the first three types are all primary, they're all categorized under primary studies. That means you go to the field, you collect data, you do your analysis. So those are all primary studies, right? But these methodological studies are not primary studies. So they are basically secondary studies. That means you're looking at existing already published literature, such as systematic reviews, primary studies have been done, both qualitative studies, quantitative studies, right? So that is what the methodological studies are. An example is what your systematic review. And then if you want to go further inside your systematic review, you can now add a meta-analysis onto it. So a meta-analysis simply means that from the results of the different primary studies that you got from your systematic review, you want to combine them together. So when you combine those results, you will now come out with a summary effect measure. All right. So for example, if you look at different cohort studies or different cohort studies that looked at the relationship between lung cancer and smoking, and then you combine all their odds ratio. Okay, so the different cohort studies, and then you combine all their relative risks and or their risk ratios, you combine them together, you get one summary effect that is called the pooled odds ratio. So I'm going to explain all these things together, but I just need you to understand how everything links together. So when you combine those things together, it's called a pooled odds ratio, or pooled relative risk, or pooled risk ratio for core studies. That pooled risk ratio is where you will find it is inside the meta analysis, right? Now, when you combine different case control studies, that is backward looking studies, that means you combine their different odds ratio in those studies, you combine them together, and then to get a pooled odds ratio, where you'll find that pooled odds ratio is inside the meta-analysis. Okay, so you cannot do a meta-analysis without doing a systematic review. You must first of all do a systematic review first. Then if you want, you can go ahead to do your meta-analysis. All right. So those are the broad categories of epidemiological studies, right? So epidemiological studies are ranked from the list, which is what the case reports, which is the case reports, which is the case report, and then um, they are all ranked together from the lowest studies designs like case reports, and then you go up until you reach the apex. The apex is what is called a systematic review. Okay, so now, like I said before, these are the 5 W's of systematic review. The first 4 have to do with descriptive epidemiology, while the last one, Y, has to do with analytic epidemiology. And remember, when you hear the word Y, you are talking about what? Cohort study. You are talking about case control study. All right, and then you can also talking about randomized control trial. They deal with Y. Y means you are trying to test a hypothesis. Okay, a hypothesis means a guess that there is a relationship between an exposure and an outcome. Right. So, what are the 3 questions that are really the focus of epidemiological studies? Number 1 is what? The burden of the disease. Epidemiological studies want the epidemiological studies the common questions are how many people in a how many persons are affected by a disease, how many persons are exposed to a disease. So how many, that means what's the burden of the disease, right? So that's the first kind of question that epidemiological studies answers. The next kind of question that epidemiological studies answers is what? The causation. What is causing the disease? What is causing the disease? So when you talk about causes, causation, you talk about analytical epidemiology, you talk about cohort study, you talk about case control study, you talk about what? Randomized control trial. All right? So that is the domain. Now, when you are looking at, sorry, when you talk about what is causing the disease, trying to identify the risk factors, then you are talking about what? Cohort study, you are talking about case control study, right? Now, the last one is what? Effectiveness. Whenever you are trying to compare the effectiveness of an intervention, which between malaria drug A and malaria drug B, which one is more effective? Then you are talking about randomized control trial. When you're trying to compare intervention A to intervention B, you are talking about randomized control trial. So you have to know the difference depending on how the question comes in the exams. All right, good. So these are the 3 broad categories so that epidemiological study designs the questions that they normally answer. So you talk about, let's talk about the Bradford-Hill criteria. Like I told you before you can say that um, um, Plasmodium falciparum is the cause of malaria, before you can establish causation, you have to make sure that the Bradford-Hill criteria is fulfilled. All right. So there are 9 components of the Bradford-Hill criterion. The first one is strength of association. So when you talk about strength of association, like I told you, the measure of strength of association in epidemiological studies is what? The odds ratio for case control study, and what the risk ratio or relative risk for cohort studies, right? Like I said, cross studies are forward-looking studies, while case control studies are backward what looking studies, right? So so if you want to measure in the number one rule in bifurcated should be that what there should be what a strength of association. So that means the odds ratio that should be that should be there should be a there should be a positive or a negative association. It cannot be just neutral. It cannot be one. The odds ratio cannot be one. The relative risk cannot be one. All right. So I'm going to explain more details on that. All right. So the second thing about it that sorry. Also, it's trying to explain what do you mean by strength. It means that what as the exposure increases, then the chance of having the disease or the chance of having an outcome also increases. So that's what is strength of association, right? There should be an association between uh, an exposure and an outcome. Sorry. So um, strength of association just means that what your relative risk and your odds ratio should be there should be a relationship between A and B. Okay, it cannot be one. Okay, it shouldn't be one because one means there is no relationship between them. All right, so that's where it comes in. Then the next one that we have here is what consistency. So that means what if you use different study designs and you do the same experiment, you will get similar results. That is what consistency generally means. And then if also different people in different locations of the world, if they do that, if they repeat the same experiments, that they also have what a similar finding like yours. All right. Now the next criteria is called specificity. So it simply means what whenever the exposure is not available, the disease or the event will not occur. Okay, so that means that the disease or the event can only occur when the exposure is available, right? So that is what specificity. Temporality simply means that what the exposure must precede the outcome or the event. So the exposure must occur prior to the event happening. That means what there must be, for example, you must be exposed to smoking for a long period of time prior to having what your lung cancer. All right. Then the next one is what your dose response relationship, or you call it the biological gradients. So the more the exposure, the more the outcome. The more the dose or the more the frequency of the exposure, the more the risk of what of the, having an event or having the outcome. So the next one is what plausibility. Okay, so that means what that is it has to make sense, common sense. Okay, so the relationship between the exposure and the outcome should make common scientific sense. All right, so there should be a plausible mechanism between the cause and the effect. All right, so it should be in line with the current scientific evidence or the current scientific knowledge. Then the next one is what coherence. So coherence between epidemiological and laboratory findings. So if you say, for example, okay, let's say like malaria. Okay, so the symptoms of malaria, fever, maybe once in a while, vomiting, headache, right? So it has to correlate with the laboratory finding of what P. falciparum, the parasite in the blood. So both the clinical symptoms and the laboratory symptoms should tally together. All right, that is what coherence. And then the next one is what experiment. So whatever relationship between exposure and outcome should be what? Validated by an experiment. Okay, that means it has to pass through. You must design a study to verify. You cannot just wake up and say this thing is the cause of this, right? So the last one is what the use of the use of analogy. Okay, so similarities between the observed association and any other association. All right, so there should be what? Agreement. There should be agreement, okay, between similar occurrences of the disease. All right, so the next thing you need to know is about the epidemiological triad. The epidemiological triad simply just tries to explain the 3 points of intervention that we can actually that epidemiologists can use to break disease or to prevent disease transmission. So you can either intervene by eliminating the agent, that is the cause of the disease. Okay, that's number one. If you cannot eliminate the cause of the disease, then you can also intervene by protecting the host. Okay, so then if you cannot protect the host, then you can work on the environment to make the environment in such a way that the disease will not even occur. All right, so the concept of epidemiological triage simply means at what different points can we intervene so that we can stop disease transmission. That is the meaning of that. All right, so looking at this, as an epidemiologist, you should know how to investigate an outbreak. So what's an outbreak? A disease outbreak simply means what? When the frequency or the occurrence of the disease is beyond the normal levels in a population. So normally you'll be asked maybe to choose a particular um, disease and then describe how you can investigate an outbreak. Okay, so there are good, if you type in Google steps in investigating an outbreak, you will see some examples from the CDC guideline. So I will not go too much in trying to explain it. So, but basically, you need to establish that there is an outbreak. That is the first one. So, how do you establish that there is an outbreak? By what? Verifying the source of information. Make sure that where you're getting the information is from a legitimate source, right? So then you take permission from the necessary from the local and national authorities to go into the place. Okay, you collect data of people that are infected. You check the hospital records and the registers, and then maybe for the previous 1 month to see if there are rise in cases beyond what normally occurs. So if you're able to determine that, then you need to um, define who you have to define an epidemiology. You have to make a definition of who is a case and who is not a case, right? So a case means what? Who can we say that when when somebody has these symptoms, or when somebody has these 1, 2, 3, 4, then we can say, okay, this person has the disease, or this person has an Ebola, and the other person does not have. So when you talk about case definition in epidemiology, there are 3 types. The first type is a case. So a case is someone that has clinical symptoms. One, has laboratory evidence. Okay, he has both clinical and laboratory evidence of the disease. That is what? A case. Now, a probable case is someone that has the clinical evidence of the disease, but that person doesn't, he has some laboratory features, but then there is no confirmation. That means what? The person has some evidence of the disease clinically, Okay, he may he may have preliminary investigations might be pointing towards a disease, but then there is no confirmatory uh, um, test. There is no confirmation yet that this person has a disease. So remember, if you are testing, you have what the preliminary test, okay, and then you have uh, confirmatory tests. So like in a HIV diagnosis, your initial test will be the rapid diagnostic test kits, right? If it becomes positive, then you need to still do a confirmatory test using what Unicode to before you can say, okay, this person has HIV. So when somebody is in between that clinical and in between clinical symptoms and then having a confirmatory test, that person is what a probable case, right? While uh, a suspected case is someone that just have just the clinical symptoms, and those symptoms might not necessarily be specific tied. It may not necessarily be specific. It might just be maybe fever, right? Let's say in the case of Ebola, anybody with fever, we are above 38 degrees centigrade, okay, and this might be a suspect, but that doesn't necessarily mean that that person uh, is uh, is a definite case, okay. So that doesn't make that person a confirmed case. So a confirmed case normally means that the person has what both the clinical evidence and the laboratory evidence. All right. So once you confirm the case, so and you need to say, okay, are we having an outbreak? Is the number increasing beyond the normal? And for that, you need to what start plotting the cases on a chart that is called the epidemic curve, right? And the pattern of that chart will also tell you the type of the epidemic. So I'll show you an example of what an epidemic curve looks like. After plotting that and you say, okay, there is an epidemic, then the next question is what is causing the epidemic? You need to make a guess. Okay, so make a guess based on the possible risk factors from literature. After you have by the time you have read your literature and you know the possible risk factors, you outline them, then you give a questionnaire, you start asking those that are infected, you start taking history, collecting their data, make a line list of all the cases, right? Make a line list of all the possible risk factors for each case. All right, then you will now calculate your relative risk for all the risk factors. The one with the highest relative risk might be the prime suspect. All right, so after doing that, you now test your hypothesis by doing an experiment. Okay, then you now initiate prevention strategies. Okay, and then you end up with surveillance. So expect to just get one case to use for practice. Maybe like you can choose cholera. Okay, you can choose Ebola. Just do some research on the internet. You'll be able to get to know how to give examples in each of these areas. All right. So we look at the epidemic curve, what it looks like. So it's simply a curve, a plot of what the each case, okay, each case is on the number of cases of people that have a disease on the y-axis, and then with time, the days or the time on the x-axis. Okay, so the nature of the epidemic curve can show you whether we are looking at a point source epidemic. A point source epidemic is the one that has, let's say, like people drank a contaminated water from a particular well, so it has a common source. Okay, so you see that the number of people that are infected will rise very quickly and reach the peak before it will now do what? Come down. You see that? So that's a point source or a common source epidemic. So we have continuous source, okay? So in a continuous source epidemic, there are multiple points of infection. So it's not localized. So you can see that the curve goes up, come down a little, goes up, doesn't have any particular pattern, it just keeps on going, right? Then you have propagated epidemic. Propagated epidemic, infection is being transmitted from one person to another. Okay, so you can see the rise in the number of cases. Okay, separated, and they are all separated by one incubation period apart. You can see this first one here. That means from the primary case. You can see this primary case, a single person under this propagated source, propagated epidemic. You will see that the first dot there is the case, the index client, the person that had the primary infection. Okay, now the space is what? The incubation period. Now after the incubation period, what? And that person was infected, the cases, the number of cases now rose. Okay, then after another incubation period again, the number of cases now increased again before it now went to a full-blown epidemic. So that is called a propagated epidemic. All right, now the last type is called the intermittent source. Intermittent source. So you can see here the infection occurs intermittently. All right, so you can see that the clusters are all separated apart. Okay, so those are the four types, the four patterns of an epidemic curve. All right, so this time around we're going to look at interpreting epidemiological studies. So you're going to see a lot of questions telling you to interpret epidemiological studies, right? So I'm going to start with the meta-analysis. Like I told you, that's the highest level of evidence, systematic review, and meta-analysis. So if you are looking at any of those papers, you are going to first of all look at the summary effect sizes. So you're going to see something like mean differences or standardized mean difference. Okay, for studies where the outcome measures are continuous variables, while for studies where the outcome measures are binary variables, you look at the words pooled odds ratio or pooled relative risk. All right, or pooled risk ratio. So those are the effect sizes that you will see in a meta-analysis. The next thing you will see is what? The forest plot. So the forest plot, I'm going to show you an example. Then then once in a while you see a funnel plot. A funnel plot will simply look at what? The distribution of the publications. It helps us to detect a publication bias. So one thing you need to know about meta-analysis is what, or in epidemiology generally, when the confidence interval is narrow, it means that the study is precise. The effect measure is very precise, as is more accurate. So generally, the higher the sample size, the larger the sample size, then the more precise the effect estimate. Okay, now another thing to look out for in interpreting meta-analysis is what? The chi-square test of heterogeneity. So if you're reading articles, you look at what they said about the heterogeneity. Heterogeneity means what? Whether the studies are actually, are they significantly different in terms of quality. All right, so the heterogeneity means that these studies are significantly different, while homogeneity means that they are all that there is no significant difference in the quality of the studies. All right, so generally we will want our studies to have low heterogeneity. That means we want them to be what? Homogeneous. So the chi-square test of heterogeneity, you look at the p-value of that chi-square heterogeneity test. So for a good study, we want the p-value of this chi-square test of heterogeneity. We want it to be insignificant. Remember, chi-square test of heterogeneity says the studies is assuming that the studies are significantly different. That means in terms of quality, they are significantly different. So, but we want a good study, a good meta-analysis, we want it to be insignificant. That means we want the p-value to be above 0.05. So, when we say a p-value is above 0.05, what does it mean? It means that if you repeat that experiment 100 times, let me interpret what p-value means. P-value simply means the amount of variation that are due to chance. The amount of variation in the results that are due to chance. Okay, so we want our study to normally have a small p-value. So if a study has a small p-value, then it means it is what? Significant. Okay, that means if you repeat that test 100 times, then it's only 5% of the time that you will get a result that is insignificant. So normally, when you talk about p-value, we normally want our p-value to be less than 0.05. So anything less than 0.05, that's 5%, is considered significant. Anything above 5% is considered insignificant. All right. So now, bringing the knowledge of p-value into this test. This is a test of heterogeneity. That means how significantly different are our studies. So on a normal day, it's assuming that the studies are significantly different. All right. So that is the default assumption, right? So if the p-value is above 0.05, it means it is what? Insignificant for the default assumption. That means what? It is insignificant for the default assumption that the studies are heterogeneous, that they are significantly different in terms of quality. That's any variation in the studies is due to chance. So in summary, if the p-value of your chi-square test of heterogeneity is above 0.05, it is good. It is good. That means what? We want it to be insignificant. So that tells us that the studies that you included in your meta-analysis, they are not significantly different from each other. Any variation in the results is not due to chance. That is the default. That is the way we want it to be. All right. So, but if you do this test and then it is below 0.05, that means it is now significant. That means that the studies are significantly different. any variation in the outcome might be due to chance. All right. Now, another effect measure that you will see in meta-analysis is called the Higgins I-square test. So now the chi-square test of heterogeneity tells us that whether the studies are heterogeneous or they are not, and it stops there. It doesn't tell us the amount of heterogeneity in those studies. So for us to know the amount of heterogeneity in those studies, we need to look at the Higgins I-square test. So now we can do the Higgins I-square test if the chi-square test of heterogeneity is below 0.05. That means it is significant. So then when it is significant, it tells us, okay, that the studies included in this meta-analysis are heterogeneous. So we now want to look at to what extent, or what is the amount of heterogeneity. If is it 25%, 0.25, then that is low. Is it 0.5? That is moderate. Or is it 0.75, which is 5%? That is what high heterogeneity. So that's simply how to interpret this when you see it in a meta-analysis paper. All right. So now the next thing we look at in the meta-analysis is called a forest plot. You can see this is how what it normally looks like. Okay. So this line here is 1 for case control and cause studies. Is normally 1. Okay. Remember, for case control and for cause studies, when your odds ratio is equal to 1, there is no association between the exposure and the outcome. For cohort studies, when your relative risk is equal to 1, there is no association between the the exposure and the outcome. So you can see, so any study that you see these lines here, whenever they touch that one line, that's that one, okay, the line here, it means that they are insignificant studies. So you can see that all the studies here generally the first, second, third, fourth, okay, the first, second, and third, they touch the line. It means they are insignificant. All right. Sorry, not insignificant. Yeah, not they touch the line. Okay, so it means that they are insignificant. All right. Now, but if you look at study number 1, 2, 3, if you look at the study number 4, it didn't touch the line, so that is a significant study. Now, if you look at the diamond is that is what we call the pooled odds ratio. The pooled odds ratio, or the pooled risk ratio, depending on the type of study that you are looking at. So in this paper now, this paper is a cohort study. So now this diamond represents the summary. This is trying to summarize all the previous odds ratios now. So now you can see that the summary, the put odds ratio, it doesn't touch the line. So that tells us that it is what? Significant, and it has a narrow confidence interval. Look at the confidence interval for the put odds ratio is what? 0.92 to 0.94. Is very narrow, and it doesn't contain 1. You see, so when the odds ratio or the risk ratio doesn't contain 1, it means it is significant. It means it is significant. All right, that means the study is significant. Now you can see in this paper, now they gave us our okay, so p-value is less than 0.0001. That means overall the study is significant, Now, the relative risk is 0.94. Now, I'm going to make out time to explain how to interpret relative risk. Okay, so in subsequent videos. Now, but generally, when the relative risk is 0.094, it means that the more exposure, the less the outcome. You see? So, but if it's more than 1, it means the more the exposure, the more the outcome. But here, you can see that it is less than 1. So that means the more the exposure, the lesser the outcome. Okay? So, now, this is Higgins I-squared. Before you go to Higgins I-squared, look at the p-value, the chi-test, the chi-square test of heterogeneity is equal to 0.05. And we said when it is above 0.05, that means the studies are what? They are heterogeneous. So this is 0.500 dots. All right, so that means we have homogeneous studies. Studies are similar, but to further check if there's any amount of what heterogeneity, the author now did the Higgins I-square test, and that Higgins I-square test came out as 0. That means there is no heterogeneity at all in the studies. So the studies are homogeneous. So they are of similar. Any variation in the effect or the outcome of the studies are not due to chance. All right. So that is how to interpret this. So here you can see the author said that overall the analysis showed a significant reduction in incidence of Parkinson's disease and Alzheimer's disease associated with a higher score of adherence to a Mediterranean diet. So you can see now in this study the exposure is what? Adherence to Mediterranean diet, while the outcome is what? As the occurrence of incidence of Parkinson disease and Alzheimer's disease. So that means the more intake of Mediterranean diet, the lesser the incidence of Parkinson's disease and Alzheimer's disease. I hope that is very, very clear. All right. So we go on to the next one. So, sorry, one more thing. So now we have talked about interpreting the forest plot for odds ratio. Sorry, the forest plot for case control studies and uh, cohort studies, right? So when the odds ratio, when the forest plot, when the pooled odds ratio touches the line, which is 1, it is insignificant, right? So now but then some studies don't have odds ratio or relative risk as their summary effect, as their summary effect. So in some studies you will see something like the mean, the standardized mean difference, or you will see mean difference. Okay, so in such studies, here this line that is 1 here will become 0. Okay, so for such studies, when the diamond line touches that 0, it means that the study is insignificant. So for such studies, whenever it crosses 0, those studies are not significant. So if you are presented with a forest plot, just look at this the summary effect, which is the diamond, and see, does it touch the line or does it not touch the line? If it touches the line, it means that the overall effect, the overall effect, the relationship between the exposure and the outcome is not significant. Okay, so that's the key takeaway from this. Also, the narrower the confidence interval, the more precise the estimate of effects. The larger the sample size, the narrower the confidence interval, and the more precise the effect estimate. Right? So now let's talk about the funnel plot. So funnel plot simply means a plot showing the distribution of publications around a particular topic. Okay, so this line here, the diagonal line on the left and on the right, they all represent the confidence interval, the 95% confidence interval. Okay, so um, the generally the studies with larger sample size are normally at the top upper part of this triangle, while studies with lesser sample size are at the lower part of this triangle. So you can see in the funnel plot on the upper side, you will see that the studies here, they are well distributed, they are balanced. But that means we have both positive and negative studies. Studies with positive results and negative results. They are well distributed on both sides, okay, of this line. So this line here, the line of no effect. So that means in the funnel plots on the upper side, there is no publication bias. Okay, so publication bias simply means the tendency to publish only positive results and minimize negative results. All right. So, but in the second funnel plot, the one on the lower side, you will see that um, at the lower left side, that means there were no smaller studies that reported um, a negative result. So here there is publication bias. You can see the line here is what? The middle line here. Studies on the right have positive results. Okay, and that means there is an effect. Studies on the left have negative results. There are no effects. So you can see that there is a bias towards producing. That means that articles that stated that there is a relationship between A and B, they are more published, while the ones that stated that there is no relationship between A and B, they are suppressed. Okay, so the importance of funnel plot is to see if from the studies that we collected, is there a publication bias, and which is not good. It is important that we avoid that. All right. So the next one is we look at what the we look at the levels of measurement in epidemiology. Right. So we have basically we have we have different types of data sets. We have the qualitative data and the quantitative data. Qualitative data are data that are not numbers, okay, while quantitative data are numbers. All right, so under quantitative data, we have two categories: numbers with decimal, all right, they are called continuous variables, and then numbers without decimal, they are called discrete variables. Discrete variables are normally whole numbers, numbers that you cannot divide. For example, you cannot say that we have 22.5 persons in the class. It can only be a whole number. So we have 22 persons in a class. You cannot say we have 22.5 persons. So that is called the discrete variable, right? Ordinal variables are ordinal data or ordinal variables. These are any data that you can rank from lowest to highest or smallest to biggest. Those are called ordinal data, right? Then you have nominal data, just basically qualitative data. They are not numbers. Okay, they are all categorical in nature. All right, so this is just like a summary. Please, you need to know this slide very well. Now, nominal data, they are categorical in nature. They are qualitative. There is no ranking. Example, you have religion, marital status, ethnicity. You can represent them using pie chart, bar chart. You can summarize them using percentage. Okay, you can summarize them using percentage. You can summarize them using modes. That means the one that occur more frequent. Okay, you can count them. All right, there is no ranking. Now, ordinal data, they are also almost similar to nominal data, except that they can be ranked. Okay, anything that can be ranked, like in your questionnaire, you have, do you agree, strongly agree, I agree, neutral, disagree, and strongly disagree. So they are summarized also using frequency distribution table, bar charts. Okay, you can summarize them. The summary measure here is median. Okay, it's median. You cannot say mean. Okay, it's median. Okay, because they are normally skewed. If you plot them on the graph, they are normally skewed. So average or mean will not be the best measure of um, effect. All right. Now, discrete data, like I told you, they are whole numbers. There's no fraction, no decimal. If you are representing discrete numbers on a bar chart, there is no okay. There is a space in between them. All right. So you can summarize them using frequency, histogram, box and whisker plot, pie chart, stem and leaf plots. Like I told you, example is the total number of persons in a class. So discrete numbers are whole numbers, so you can count them. So you can summarize them using the summary measure can be mode, it can be median. All right. Now, continuous data are anything that has this decimal point. They are divisible till the minutest. Okay, they have decimal points. They are all numbers. You can visualize them using histograms, line graphs. Okay, example is weight, temperature, height. So they are all quantitative data. So you can summarize them using mean, median, mode, range, interquartile, range. Also know that a histogram can be used to summarize both discrete and continuous data. So this is an example of a histogram. You can see here there is no space in between them, right? Okay, so histogram for ordinal data showing it is ranked. Okay, so now sorry, this should be a bar chart, not histogram. So in a bar chart can be used to represent categorical data. It can also be used to represent ordinal data. So but the only difference here is that if you are representing ordinal data, because they are ranked, you don't give any space in the bar chart. Okay, so it also looks like a histogram. You don't give any space to show that they are ranked. But if it is a nominal data that doesn't have any ranking, you give space in between the bar charts. All right. Okay. All right. So this is how you can represent nominal data. Use frequency table, proportion. Then all your cross-sectional studies most times use frequency table and pie chart that you can use to represent them. You can also use this to represent ordinal data too. Okay, so this is how a bar chart for nominal data looks. You can see there is a space in between them just to show that they are not ranked together. All right, so this is a box and whisker plot. So you can be asked to interpret. So just look at the labels, the minimum, the maximum, the median, the first quartile range, and the third quartile range. So these are the critical points to look out for, okay, when you're asked to interpret. So you can just give you values here and ask you. Also remember, you can calculate the interquartile range. That means the value in the third quartile range minus the value in the first quartile range. All right, so this brings me to the end of this presentation. So in the next video, we're going to look at your odds ratio, the calculations. We're going to look at the relative risk, the risk ratio, how to calculate them. We're going to look at your laboratory test sensitivity and specificity. Okay, we're going to look at them. We're going to look at how to interpret logistic regression, how to interpret linear regression. I think, and that will bring us to the end of this series. All right, so thank you so much. Remain blessed. I'll see you in the next video.